70 kilometers off the coast of Guangdong province, in water more than 50 meters deep, there is a structure the size of a small stadium sitting on the open ocean, and it is not attached to the seafloor at all. No concrete foundation, no steel pile driven into the seabed. It simply floats, tethered by mooring lines, rising and falling with every swell that passes underneath it. On top of that platform sits a single wind turbine rated at 16 megawatts, and by itself, that one machine generates enough electricity every year to power roughly 24,000 households. It was installed on May 2, 2026, and Chinese state media is calling it the largest single-unit floating wind turbine platform ever built. It will not hold that title for long. A Chinese manufacturer has already announced a turbine 3 times its size, designed specifically to survive direct typhoon strikes, floating in the same waters. Wind turbines have gotten enormous before. Plenty of viral videos have shown you spinning blades longer than football fields sitting on a normal foundation planted in the seabed. This is a different story, and a genuinely stranger engineering problem. Imagine trying to keep a machine the height of a skyscraper, with blades sweeping an area larger than several soccer fields, generating stable, grid-ready electricity 24 hours a day, while the entire structure it stands on is constantly rising, falling, and tilting with the waves beneath it, never once touching solid ground. That is not a hypothetical. It is exactly what is happening off the coast of China right now, at a scale nobody had attempted just a few years ago. By the end of this video, you will understand exactly how you keep a turbine this massive, stable, and generating power while it bobs on the sea, why fixed turbines simply cannot go where these can, and how far this technology realistically is from actually mattering at global scale. If you like videos about the technology quietly reshaping how the world works, hit like and subscribe so you do not miss what is coming. Let's start with the wall that made floating turbines necessary in the first place. Every offshore wind turbine built before floating technology existed had to be bolted directly to the ocean floor, using massive steel or concrete foundations driven or sunk into the seabed. That approach works fine in shallow coastal water, where the foundation only has to reach down a few dozen meters before hitting bottom, but it runs into a hard economic wall as the seabed drops away. Once water depth passes somewhere around 50 to 60 meters, building a fixed foundation stops making financial sense. The foundation has to get taller, heavier, and more expensive at a rate that outpaces the extra electricity you get from the stronger, steadier winds found farther out to sea, until eventually the numbers simply do not work anymore, no matter how good the wind resource is above the water. The problem is that most of the planet's best offshore wind does not sit in that shallow, developer-friendly zone close to shore. Research from America's National Renewable Energy Laboratory has estimated that the wind resource sitting in U.S. coastal waters deeper than 30 meters could theoretically generate more than 3,200 terawatt-hours of electricity a year, equivalent to roughly 90% of the entire country's current energy use, and a huge share of that resource sits specifically in water too deep for a fixed foundation to ever reach economically. Most of that deepwater wind resource sits between roughly 37 and 93 kilometers offshore, exactly the kind of distance and depth combination that made it functionally invisible to the offshore wind industry for its entire first 3 decades. For decades, that meant some of the strongest, most consistent wind on the planet was completely locked away, visible on every wind resource map engineers ever drew, but genuinely unreachable by the technology available to harvest it. Floating platforms exist to break that lock. Instead of anchoring the turbine tower itself to the seabed, engineers anchor a buoyant platform, and the turbine sits on top of that platform instead, held roughly in place by mooring lines and anchors rather than a rigid foundation. There are a few different ways to build that buoyant base. A spar design achieves stability the way a fishing bobber does, with a long, deep, heavily ballasted tube that sits low in the water and stays upright through sheer weight distribution, though its deep draft limits which ports can actually handle it. A semi-submersible design, the type used in most of China's recent projects, spreads its buoyancy across a wider structure at the surface, trading some stability for a shallower draft that makes it easier to tow, assemble, and bring into port for maintenance, at the cost of more exposure to wave action since more of the structure sits above the waterline. A tension leg platform achieves stability through tight, vertically pulled mooring lines instead of pure buoyancy, offering excellent stability once installed at the cost of being genuinely difficult and risky to assemble and adjust before the mooring tension is fully set. Whichever design a company picks, the entire structure then has to survive something a fixed turbine never has to deal with: constant motion. The platform pitches, rolls, and heaves with every wave, and the turbine, the blades, the gearbox, the generator, all of it has to keep functioning normally while genuinely floating and swaying on open ocean, a problem nobody had to seriously solve at commercial scale until floating wind came along. China's entry into this specific technology did not start with the machine sitting off Guangdong right now. It started in 2024, when Mingyang Smart Energy, one of the country's largest private wind turbine manufacturers, launched its Ocean X platform at the Qingzhou IV offshore wind farm, also off Yangjiang in Guangdong. Ocean X carried two separate 8.3 megawatt turbines mounted on a single V-shaped floating structure, adding up to 16.6 megawatts combined, and it became the proof of concept that convinced the rest of China's offshore wind industry this technology was ready to move past small demonstration projects. Mingyang was not the only company chasing the record either. China Railway Rolling Stock Corporation, better known as CROOC, a company more famous for building high-speed trains than wind turbines, installed its own 20-megawatt Qihang prototype for testing in Shandong province, with a rotor stretching 260 meters across and a hub sitting 161 meters above the water, at the time the single most powerful wind turbine of any kind, floating or fixed, undergoing real-world testing anywhere on Earth. Then, on May 2, 2026, state-owned China Three Gorges Corporation, the company perhaps best known for building the Three Gorges Dam, installed what it calls the Sanxia Linghang platform, translating roughly to Three Gorges Pilot, at a site more than 70 kilometers off Yangjiang, in water exceeding 50 meters deep. Unlike Mingyang's twin turbine Ocean X design, Sanxia Linghang carries a single 16-megawatt turbine on its platform, and the company is calling it the world's largest single-unit floating wind turbine platform, specifically because it packs that much capacity onto one turbine rather than splitting the load across two rotors. Once fully operational, the platform is expected to generate around 44.65 gigawatt-hours of electricity every year, enough to supply approximately 24,000 households, delivering nearly 3 times the output of its immediate predecessor while cutting the cost per kilowatt by more than half, according to the developer, and achieving what China Three Gorges describes as full localization of every key piece of equipment involved, meaning the entire supply chain behind it, from the massive floating hull to the turbine's internal components, was sourced and manufactured domestically rather than depending on foreign suppliers for critical parts. That cost reduction number matters more than it might sound like on its own. Floating wind has historically been significantly more expensive to build than fixed-bottom offshore wind, precisely because every part of the engineering, from the platform itself, to the specialized mooring systems, to the dynamic power cables that have to flex and twist with the platform's motion, instead of sitting rigidly in place, is more complex and less standardized than what a conventional bottom-fixed turbine needs. Cutting that cost by more than half in a single generational leap, while simultaneously localizing the entire supply chain, is the kind of improvement that turns a technology from an expensive demonstration project into something an energy company might actually build dozens of, not just one. And China is already planning for dozens, then hundreds. In October 2025, Mingyang unveiled plans for what it is calling the world's largest floating offshore wind turbine, a genuinely startling 50-megawatt design, more than 3 times the capacity of the Sanxia Linghang unit that had not even gone into the water yet at the time of the announcement. The design carries 2 separate 25-megawatt rotors mounted on a shared V-shaped tower, echoing the twin turbine layout of the original Ocean X platform, but at a scale that is difficult to picture without the actual numbers. Each rotor spans roughly 290 meters, longer than 3 football fields laid end to end, mounted on a hub standing around 190 meters above the water. Mingyang says the design is specifically engineered to keep generating power through typhoon-force winds and heavy rainstorms, rather than simply shutting down and riding out the storm. A genuinely important distinction for a turbine meant to operate in exactly the stretch of ocean, the South China Sea and Western Pacific, that produces some of the most powerful tropical storms on the planet every single year. The company says it expects to begin mass production in Guangdong Province in 2026, eventually scaling to as many as 150 units a year, and has quoted a production cost target as low as $1,300 per kilowatt, a figure that, if it holds up in real deployment, would undercut most Western offshore wind manufacturers by a wide margin. Mingyang has also announced plans to invest up to 1.5 billion British pounds building a manufacturing facility in Scotland, specifically to bring this floating technology to the UK and European market, with a site near Inverness currently the preferred location, a clear signal that this is not purely a domestic Chinese project. None of this is happening in isolation from China's broader offshore wind build-out, which is worth understanding to see how floating technology actually fits into the bigger picture. By the end of 2025, China's total offshore wind capacity, floating and fixed bottom combined, had reached roughly 48.4 gigawatts, and the country accounted for 78% of all new offshore wind capacity connected to any grid on Earth that year, extending a streak of leading the world in new offshore wind installations for 8 consecutive years. China now holds more than half of all operating offshore wind capacity worldwide, and under its current 5-year plan, the government is targeting more than 100 gigawatts of cumulative offshore wind capacity by 2030, with a specific, deliberate push toward what Chinese energy planners classify as deep-sea wind, water deeper than 50 meters, and far offshore wind, sites more than 65 kilometers from the coast, exactly the category of site floating platforms exist to unlock. Floating wind specifically is still a small fraction of that broader offshore total. As of the most recent global tallies, floating wind capacity worldwide sits at less than 300 megawatts, out of roughly 83 gigawatts of total offshore wind capacity installed globally, meaning floating turbines still make up less than 1% of the entire offshore wind industry, even after everything you just heard about China's recent breakthroughs. Every one of these Chinese milestones, the 16.6 megawatt Ocean X, the 20 megawatt Qihang, the 16 megawatt Sanxia Linghang, the 50 megawatt concept still in development, is still fundamentally a demonstration project or an early production unit, not evidence of a mature industry already operating at scale. It would be dishonest to end this story sounding like floating wind has already solved every problem standing between it and dominating global offshore energy, because it genuinely has not. Every floating platform still has to survive decades of constant wave motion without its mooring lines fatiguing, its dynamic power cables cracking from repeated flexing, or its anchors slowly dragging across the seabed, and none of the turbines discussed in this video have been in the water anywhere close to long enough to prove that kind of multi-decade durability the way fixed-bottom turbines, which have been operating commercially since the early 1990s, already have. Maintenance is also a genuinely harder problem 70 kilometers offshore in 50 meters of water than it is a few kilometers from shore in a fixed installation. Every repair trip costs more, takes longer, and depends more heavily on weather windows calm enough to safely work on a platform that never stops moving. Mingyang's typhoon-resistant claims for its 50-megawatt design are, as of this video, still design specifications and early-stage engineering targets, not results from an actual typhoon season survived in open water, and the difference between a turbine engineered to handle typhoon-force loads on paper and one that has actually ridden out a direct hit is exactly the kind of gap that tends to only get closed by time and real storms, not press releases. China is also not operating in a vacuum here, even if it is currently moving faster than anyone else. Norway's Hywind Scotland, switched on in 2017, was the world's first operating floating wind farm, 5 turbines totaling just 30 megawatts, a fraction of the capacity a single Chinese floating turbine now generates on its own, less than a decade later, but a genuinely important first proof that the entire concept could work commercially at all, rather than staying a lab curiosity. The UK, Japan, South Korea, and the United States are all pursuing their own floating wind programs, specifically because each of them has coastlines sitting over water too deep for fixed-bottom turbines to ever reach. The US West Coast being a particularly clear example, where the Pacific seafloor drops away quickly enough that floating platforms are essentially the only realistic path to offshore wind at any meaningful scale. What China has clearly done differently is move faster from single demonstration units toward full domestic manufacturing capacity and export ambitions, exactly the same playbook the country has already run in fixed-bottom offshore wind, solar panels, and batteries. Prove a technology works, then build the factories to make it cheap enough to deploy everywhere else too. Step back, and the actual story here is less about one enormous turbine off the coast of Guangdong and more about an entire category of ocean that used to be permanently off-limits to wind power, quietly becoming reachable. Fixed-bottom turbines hit a wall at around 50 or 60 meters of water depth that no amount of engineering ambition was ever going to move, because at some point, the foundation itself simply costs more than the electricity above it is worth. Floating platforms do not solve that problem by making the ocean shallower. They solve it by refusing to touch the bottom at all, and China, in the space of about 2 years, has gone from a single demonstration platform to a company promising mass production of turbines 3 times that size, engineered specifically to survive the very storms that make the deep water off its own coastline so valuable in the first place. If this video showed you a piece of the energy world you had not seen coming, hit like, subscribe, and turn on notifications so you catch the next one. And here's a question for the comments. With floating wind still sitting at under 1% of global offshore capacity today, do you think China's manufacturing scale and cost advantage turns this into the next industry it comes to dominate the way it already has with solar and batteries? Or is the deep ocean simply too harsh an environment for any single country to run